All right, class, this is a continuation of the Chapter 3.2 lecture for a remote day of learning. We're going to talk more about Lewis structures, and then from Lewis structures, we're going to apply another theory called valence electron pair repulsion theory to determine the geometry of the molecule. So, last time we talked about ionic and covalent bonding, and this last slide here, which is the first slide of this lecture, just shows you what the macro properties are for ionic and covalent compounds. Again, ionic compounds are held by electrostatic attractions, so they have very high melting and boiling points, and generally are solids at room temperature, whereas covalent compounds can be solids, liquid, or gases because the forces are generally not as strong. So a new lecture today, we're starting on drawing Lewis structures, and there are these guidelines to go by. What I'm going to do is I'm going to draw a few Lewis structures, and then we'll talk about the different I'm going to show you the easiest way to draw a Lewis structure, okay? And that'll make it easier for you on exam or if you're taking the lab. But one thing I do want to point out, this is really important that a lot of students miss, is that when you draw a Lewis structure, the the least electronegative element or atom goes in the center, all right? The least electronegative. So again, that's why it's important that you know the electronegativity table. And hydrogen can never be the central atom. It always occupies the a terminal position. And the halogens occupy terminal positions except when one or more electronegative elements are present. So when more electronegative elements are present, all right? And then carbon often forms a chain. That's why life is based on carbon on this planet, because it's very easy for carbon to form long chains. So determine the number of valence electrons. So this is the best way to do a problem, is first of all count up your total number of valence electrons. So what they're saying here is if you have carbon dioxide, that the first thing you do is you total all the valence electrons in this molecule. So carbon is in group 14, it has 4 valence electrons, and oxygen, you have 2 of them, and oxygen is in group 16, and everything in group 16 has 6 valence electrons. So 6 times 2 is 12, plus 4 is 16, so 16 valence electrons. All right, so then they talk about polyatomic ions. So let's look at ammonia, the ammonium ion, NH4 positive. This is one of the polyatomic ions, NH4 positive. All right, so nitrogen in group 15 has 5 valence electrons, 4 hydrogen. Each hydrogen in group 1 has 1 valence electron. So we're dealing with 9 valence electrons. Oops, I don't know what that is. 9 valence electrons. But because it's a positive ion, you have to subtract 1 electron. So you have 8 valence electrons. I'll just say VE there for short. So for positive ions, you remove electrons. For negative ions, you add. So like if we had nitrate, then we would have 5 for nitrogen plus 3 times 6 for the oxygen. And then we've got to add an electron for the negative charge here. And that would equal 24 valence electrons. So that's what they're talking about in this slide. Next slide says connect the central atom to each of the surrounding atoms with single bonds. Next, place the electrons as lone pairs around the terminal atoms to complete the octet for each. So what this is saying is that if we have something like methane, CH4, that this has 4 valence electrons, and then we have 4 hydrogen. Each one has 1 valence electron. If we add that up, we have 8 valence electrons. So carbon goes in the center because hydrogen can never go in the center. And you know that there is a bond between each hydrogen and carbon. So that's what the single line represents. So another way to draw this, if you're first starting out, you may want to just use dots. And you know that the total number is 8 dots. And what's happening here is there's a hydrogen here, and a hydrogen on this side, and a hydrogen on this side, and a hydrogen on this side. So each hydrogen feels like it has 2 electrons, and the carbon feels like it has 8 electrons. So carbon's satisfied with the octet rule, hydrogen's satisfied with the duet rule. It only wants 2 in the first shell to be full. And so you can write it this way with dots, or what they're talking about here is connect with single bonds. So these shared pairs that you see here and here and here and here, they're represented by these lines, which represents a single bond, which is the shortest and strongest, the longest and weakest of the covalent bonds. All right. What do they mean by terminal? What do they mean by since after terminal atom to octet, following the central atom octet, the valence electrons are still available. So what this is saying is that, like if we have HF, hydrogen fluoride, that's a total of 1 plus 7 valence electrons. That's 8 valence electrons. So hydrogen can't be the central atom. So fluorine's going to be the central atom. It's going to have 8 around it. And then the hydrogen's attached to the fluorine like so. So there's a single bond there. These are called lone pairs. Lone pairs are non-bonding pairs. And they're important because they show that fluorine has a total of 8 valence electrons around it. And then hydrogen's satisfied with 2. So there's the 2 for that. And if you wanted to clean this up, you could write H with a single bonded line like so. Remember, a single bond represents a shared pair. It represents a shared pair. And then there are 3 lone pairs on the fluorine like so. And then one other thing to add to this is that fluorine's more electronegative, so you could put a partially negative on this end of the bond, or partially positive on this end of the bond, and a partially negative on this end of the bond. Or if you like the arrow, you can do an arrow pointing in that direction to show that fluorine is pulling, this is a polar covalent bond, and that the electrons are spending more time around the fluorine than the hydrogen. All right, if the octet rule is not satisfied for all atoms, move 1 or more lone pairs on a terminal atom to make the bond with the central atom. All right, continue to shift the electrons until all atoms have an octet. After you are satisfied with the Lewis structure that you've constructed, perform a final electron count. And I'll show you an example of that in a second. Here's a good example. So they've already done it for us. So let's look at carbon dioxide. So first of all, you got to draw a skeletal structure. And here's your possibilities, this or this. But because carbon is the least electronegative, 2.5 versus 3.5 for carbon, carbon's going to be the central atom, and the oxygens are going to be attached to the carbon like so. So that's what they say. The resulting structure should be this. Okay, least electronegative element goes in the middle. Everything else goes around it. And you say, well, how am I supposed to know that? Well, you know the trend is electronegativity increases as you go across, and carbon's here and oxygen's here on the periodic table. So oxygen's more electronegative than carbon. Like I said, these come up so frequently, I would memorize them. They come up so frequently, I would memorize them. So they say, there's at least 1 bond between here and here. The total number of valence electrons here is 4 plus, because it's in group 14, carbon, plus 2 times 6 for oxygen. So we're dealing with a 16 valence electron system. So let's do this. Let's go, there's one bond here. Let's go 3 lone pairs on each oxygen, like so. Okay, let's count up our total number of valence electrons. There's 2, 4, 6, and then 8 if you count the bond between the oxygen and carbon. Same thing on the other side. And so each oxygen feels like it has 8. How many does carbon feel like it has right now? Well, the answer is 4. It's got 2 here and then 2 here. Needs 8. So this is what it says. You move the electrons from the terminal in between the terminal and the central atom, like so. By doing that, you now have 2 lone pairs or 2 bonding pairs coming off of the carbon, and now you only have 2 lone pairs on each oxygen, like so. Okay, so when you do that, it doesn't change the number on the oxygen. The oxygen still has 2, 4, 6, 8. Same thing over here, 2, 4, 6, 8. And now carbon, with its 2 double bonds on both sides, that gives it 8 electrons too. So everything is satisfied. Oxygens have 8. Again, if you count all of that, oxygens have 8. This oxygen has 8. And this carbon has 8. So we know that is the proper Lewis structure for carbon dioxide. So they do the same thing. They total up the total number of valence electrons. Okay. Then they do the skeletal structure. Carbon's in the center because of the lower electronegativity. They put all 16 electrons into the system. Remember, a line represents a shared pair. Carbon's not satisfied. It only has 4 electrons around it. So we shift a lone pair from the oxygen to the carbon, and that allows carbon to have a total of 8 electrons around it. And just remember, a double bond is shorter and stronger than a single bond. And in the end, everything feels like it has 8. Carbon feels like it has 8. Oxygen feels like it has 8. This oxygen feels like it has 8. We recheck the work one more time. Let's make sure our electrons are right. 1, 2, 3, 4. And then there's 2 there and 2 there, so that's 8. And then 1, 2, 3, 4, 2 there and 2 there is 8. That's a total of 16 valence electrons. That's what we have. And that's what we should have, and everything feels like it has 8, so we're in good shape. One last thing I would tell you to do, I would tell you to evaluate the bond between the carbon and the oxygen. This is oxygen being more electronegative. The electrons are being pulled towards the more electronegative oxygens. So we do have polar covalent bonds here between the carbon and the oxygen. All right, so here's the next one. So you may want to stop the video at this point and see if you can do it, and then go through the slides to make sure that you can do it correctly. Okay, the first thing we look at is the ion. We see carbon has 4 valence electrons. We have oxygen, there's 3 of them. Each oxygen has 6 valence electrons. And then, don't forget, if this is a negative ion, we got to add 2 more electrons. So if we add 2 more electrons, we get 2 plus 18 plus 4, that's 24 valence electrons. We know carbon goes in the center because it's the least electronegative, and we put the oxygens around the carbon like so. We know there's at least 1 bond between the carbon and the oxygen, so we go on and put in some single bonds, and then we put in our lone pairs around each oxygen. so that each oxygen feels like it has 8. All right, and when we do that, each oxygen is satisfied with 8, but how many does carbon feel like it has around it? Well, it's 6. So what we've learned is you take a lone pair and you slide it in between the carbon and the oxygen. And that allows you to satisfy carbon with also satisfying the oxygen. So they did the lone pair, instead of on this side here, they did it from the top, but you now have a double bond between the carbon and the oxygen. So carbon satisfied, each oxygen is satisfied with 8, and the double bonded oxygen is satisfied. It's got 2, 4, and then each one of those lines is a shared pair, so 6, 8. Another thing to remember here, it's really important that when you're doing an ion or a negative ion, you put it in brackets and you put the charge outside the brackets in the upper right hand corner. And what that does, any chemist looking at this, when he sees the brackets in the outside -2 charge, they know that 2 electrons have been added to this system. So that's how we get 24 electrons instead of 22. Now, there's probably some of you asking, why couldn't the double bond be here and this be the single bond and this be the single bond? Or why couldn't the double bond be here and this be the single bond, this be the single bond? Well, it can. It can happen, and hopefully they show us that. Let's see if they do. No, they don't. We talked about this in class, but none of the structures are correct. There'll be 3 of them, one with the double bond here, one with one here, and one with one here. We did it in class. We called it resonance, and we said that none of these are correct. That when we measure the distance between the carbon and the oxygen on any of these bonds, that it's exactly the same distance. So if this was correct, this would be shorter between the carbon and the oxygen, and it's not. And let me try a different pen here. They're all the same length, so we know this Lewis's theory is failing here. That 2 other structures are required, and you put double-headed arrows between the 2 structures where the double bond is on a different oxygen. So there's 3 structures. It's called resonance. Lewis's theory is failing. None of them are correct, but that's the best we can do. All right, so let's do the Lewis structures for these. So again, I'd tell you to stop the video, try to do them on your own, and then see if you get the same answer as I get. So the first one, water, this is the process right here. So let me use a little bit thicker pen maybe. All right, so the first thing you do is add up your total number of valence electrons. 2 times 1 for hydrogen plus 6 for oxygen equals 8 valence electrons. Hydrogen can never be the central atom, so and we know there's at least one bond between the hydrogen and oxygen like that. So that means there's going to be a lone pair here and a lone pair here, and that's 8 electrons. A line represents a shared pair, so there's 2, and then there's another 2 here, and then 2 lone pairs. These are called lone pairs or non-bonding pairs. So there's a total of my 8 electrons. Oxygen feels like it has a total of 8 around it, and each hydrogen feels like it has a total of 2 around it, which is satisfied. So that is the proper Lewis structure for water. Just an H, oxygen, 2 lone pairs, and then another hydrogen. Okay, ammonia, let's look at this one. Nitrogen group 15 has 5 valence electrons. We've got 3 hydrogen, each one has 1. We add that up, we get 8 valence electrons again. Nitrogen goes in the center because hydrogen can never be the central atom. The hydrogens are attached to the nitrogen like so. So we've used up 6 electrons. Each line is a single bond, which represents a shared pair of electrons. So the other 2 electrons must go on the nitrogen. So nitrogen has 8 valence electrons around it. So it's satisfied with 8. Each hydrogen satisfied with 2. That is the proper Lewis structure for ammonia. Now, I didn't do this up here. Let's do this. I would draw some arrows like this to the more electronegative to show that this is polar covalent bonding. Same thing here. Nitrogen's more electronegative than hydrogen, so the arrows are pointing towards the more electronegative nitrogen. It's just good practice to think about it. Carbon dioxide, we've already done that one. It was 4 for this plus 2 times 6 for this. We're looking at 16 valence electrons, and we end up with a double bond here and a double bond here, lone pair here, lone pairs here, and that's a total of 16 electrons. Ammonium ion, you got 5 for this, 4 times 1 for this. Got to subtract 1 though. Why subtract 1? Because it's a positive ion. So we are looking at a total of 8 valence electrons. Nitrogen goes in the center. You know there's a hydrogen bonded to each one of the, with a single bond to the nitrogen. And then because it's an ion, you should put it in brackets and the charge outside the brackets. So that's what the ammonium ion looks like. Last one, you've got a total of 2 times 5. You got a total of 10 valence electrons. Everything has to feel like it has 8. You end up with the triple bond between the nitrogens and a lone pair on each nitrogen like that. So there's my 10 electrons. 2 times 5 is 10. This nitrogen feels like it has 8. And this nitrogen feels like it has 8. That's the first time we've seen a triple bond. A triple bond is 3 bonding pairs. There's a total of 6 electrons in those 3. You know, when you count these up, this is 2, this is 2, and this is 2. So there's 6 bonding electrons, and we call this a triple bond. There's 3 shared pairs there. And the electronegativity difference here would be 0, so this is a true pure covalent bond. Non-polar is what we would say. All right. Hopefully you got those correct. If not, email me. Let's talk about it. All right, we just said single bonds, 1 pair of electrons being shared between 2 atoms. It is the longest and weakest of the bonds, of the covalent bonds. Then we have a double bond, which is 2 shared pairs. So like again, we have carbon dioxide, that's a shared pair, 2 shared pairs with that oxygen, 2 shared pairs with this one. They are shorter and stronger than a single bond. And then we just saw nitrogen, triple bond between 2 nitrogens. And that is the shortest and strongest of the covalent bonds. Make sure you know that, because I do test between single bond length or energy or strength of bond to triple bond, which is again strongest of the covalent bonds and also the shortest. So bond energy, that's what this is showing. Triple bond has the greatest energy, then this double bond's a little less than, and the single bond is less than the double bond. And bond length, single bond is the longest, then we go to a little shorter double bond, and then we go to the shortest, the triple bond. All right, write the Lewis structure of carbonate. Now we've actually seen this, and they said resonance. So let's just go on and draw it. Again, what I expect for you to be able to do at this point is to say 4 valence electrons for carbon, 3 times 6 for oxygen, plus you add the 2 extra for the charge, and that's 24 valence electrons. I expect you to be able to put a carbon here, single bond. I'll put a double bond here. No, I've already done. All right, I'll put a double bond there, single bond here, single bond here to the oxygens. We know that each oxygen has to have 8, so we're putting our lone pairs in. And then because we've added 2 extra electrons, we should put this in brackets and put a -2 charge outside the brackets. Now, when you look at that structure, you can see that each oxygen has 8 valence electrons. Carbon has 8 valence electrons, and we have put in 24 electrons, 8 around each one of these oxygens. So resonance is, and we've talked about it, but you could, instead of putting the double bond on the right, you could put it on the center oxygen and single bonds like this. And so if you do that, then there's 3 lone pairs on this oxygen, 3 lone pairs on the single bonded oxygen here, and there's only 2 lone pairs on that double bonded oxygen in the center. So that's another possible Lewis structure. We are following the rules for that Lewis put forward, and we're coming up with more than one structure. And then we could come up with a third one. And the third one would be carbon in the center, single bond in the center oxygen, single bond on the left, single bond there, single bond here means 3 lone pairs on that oxygen, then a double bonded oxygen there with 2 lone pairs, and that would be -2 charge. So this is called resonance, and again, it's when Lewis's theory is failing. None of these are correct. None of them are correct. But we have to draw all 3 structures, and by drawing all 3, anyone looking at this will go, oh, resonance is occurring. So it happens, and it's recognizable because there's more than one structure drawn here. And it is important. And the actual bond length is not a double bond, it's not a single bond. It's a different length altogether. It's somewhere between a double and a single, but it's not single or double. All right, so they do a much better job drawing the structure than me, but I will say they have a mistake here. This should be in brackets, 2 negative here. This should be in brackets, 2 negative here. This should be in brackets, 2 negative here. Make sure you put the brackets around an ion. That signifies that there's some alteration there. All right, we also have compounds that do not follow the octet rule. So beryllium. Beryllium is number 4, the 4th element on the periodic table. If we look at beryllium, it's got 2 electrons in the first shell and it has 2 electrons in the second shell. Beryllium would typically lose 2 electrons if it was bonding with a nonmetal, like a strong nonmetal, but and it would have a full outer shell of 2, which is fine because that's all the outer shell can hold. The first shell can hold is 2 electrons. So beryllium does not follow the octet rule. It is satisfied with creating only 1 bond between these 2 hydrogens, and beryllium feels like it only has 4 electrons around it. So that's called an incomplete octet. So incomplete means we are not following the octet rule. You see this with hydrogen, you see it with helium, you see it with lithium, beryllium, and a lot of times you see it with boron as well. So these are the ones that typically do not follow the octet rule. And it makes sense because if these are losing electrons, they're going back to just the second shell. Now boron actually doesn't lose the electron. Boron, though, doesn't feel like it needs to have 8 around it. It's satisfied with 6. So common compound with boron is boron trifluoride, and it's actually boron bonded to a fluorine, bonded to a fluorine, bonded to a fluorine, and then the fluorines each have their 3 lone pairs around it, and that's it. And boron satisfied with 6 electrons. All right, next one is the odd electron model. So, like when you look at nitric oxide, this has 5 valence electrons, this has 6, total of 11. That's an odd number. That's the first time we've seen an odd number of valence electrons. So it's impossible to make it so that everything feels like it has 8. But what you want to think about is the thing that's more electronegative wants to have 8. It's going to pull more likely to have 8 than the thing that's least electronegative. So the odd electron will probably go on the least electronegative element. All right, so that's the way to remember that. If you get an odd electron model and you're trying to figure out where does the odd electron go, it usually goes on the least electronegative element. All right, this one is cool. This is the expanded octet. Here's how you know you're dealing with the expanded octet. If we have this substance and there are 5 things bonded to the phosphorus, because that's what this is saying, 5 fluorines are bonded to the phosphorus, you know that's not following the octet rule. You know it's not, because if you count up the bonds here, that's 2, 4, 6, 8, 10. That's beyond the octet rule. So you say, well, how can that be? Well, once we get to the 3rd period and beyond, there's always a D sublevel that has not been filled yet. So remember when we go through the electron configurations, we have 1s2, 2s2, 2p6, 3s2, 3p6. Then we did the 4s2, and then we started the transition metals at 3d. So the D at phosphorus, we haven't added any electrons to the 3d. So phosphorus is able to use these unfilled 3d electrons to have an expanded octet. Same thing for arsenic right below it. It has an unfilled 4D. So arsenic is AS. It has an unfilled 4D, so it can also have an expanded octet. You do not see an expanded octet with anything in period 1 or 2. 1 or 2, because there's no D sublevel to accept those extra electrons. Main thing here is these all have to have 8. The terminal fluorines all have to have 8, and they do. And then when you do that, and you know there's at least 5 things bonded to the central atom, that's going to have 10 around it, and it doesn't follow the octet rule. So this section is where we take everything we've learned about Lewis structure, and from looking at a Lewis structure, we apply valence shell electron pair repulsion theory, and from that we're able to determine the 3-dimensional geometry of the molecule. So that's what's neat about this. Draw a good Lewis structure, and from that Lewis structure and applying VSEPR theory to it, you can determine the 3-dimensional geometry. So it says covalent bond is directional. They have a specific orientation. And so that's what we're going to focus on. Ionic bonds have electrostatic forces which are not specific to orientation. So that's why if you go back and look at that sodium chloride, it's just a cube of sodium and chloride ions all bonded together. Well, covalent bonds have direction. They're going to bond at certain angles because it's carbon, and then it's bonded at certain angles with hydrogen. It's not a cube of just chlorine or carbon and hydrogen atoms. It's got a direction to the bond, and that's going to give it a 3-dimensional geometry. So valence shell, that's what we've been dealing with, the valence shell, the outer shell, the electrons in the outer shell, so electron pairs, and then repulsion. So what this is saying is that when we do the Lewis structure for beryllium hydride, which was just done in the previous slide, we said it was incomplete octet. It did not follow the octet rule. These electron pairs do not want to be anywhere near each other. Now, these aren't the worst. These are called bonding electron pairs, but they don't want to be anywhere near each other. So that's why you never see the structure for beryllium hydride to look like this, a hydrogen here and a hydrogen here, because the angle between those two hydrogens would be 90 degrees. So what kind of geometry do you use to keep the electrons as far away from each other as possible? Well, you put them 180 degrees from each other, which makes this molecule linear. So that's its geometry. Okay? So that's what you need to be thinking about is how do I place the electron pairs around the central atom in such a way as to minimize electron-electron repulsion or electron-pair repulsion. So if you only have two electron pairs, they need to be 180 degrees from each other to minimize the repulsion. You would never see it this way, 90 degrees. And then, so here's the things you need to know. You need to know this angle. You need to know the name of that geometry, linear. All right, the next question is, how do you keep three things as far away from each other as possible? So think about it before you flip to the next slide. Stop and pause. But how do you keep three things as far away from each other as possible? Well, that's called trigonal planar. So we actually did this one just a minute ago. Boron trifluoride. You have three fluorines bonded to the boron. There's a shared pair here, a shared pair here, and a shared pair here. So how do you keep these bonding pairs as far away from each other as possible? Well, you arrange them in the order of a triangle. So that's a triangle here. And then you know that the angle between here and here is 120 degrees. This is 120, 120, 120, which is 360. That's the full circle. So you need to know the angle. You need to know what the name of this geometry is, trigonal planar. It's flat. That's how you keep three bonding pairs as far away from each other as possible. And you're going to have to memorize these. You are going to have to memorize these. You're going to do a Lewis structure. Then you're going to, based on the Lewis structure, look at the electrons coming off the central atom. And you either have bonding pairs or lone pairs on the central atom, and you want to keep them as far away from each other as possible. And the most repulsive is the lone pairs. Lone pairs take precedent over the bonding pairs. Okay, next one is methane. So methane has a total of 8 valence electrons. When you do the Lewis structure, it's going to look like this. This is what you would do. All right, that's my Lewis structure. Now, if you just stop there, you'd say methane looks like a cross, that it's 90 degrees between the hydrogens here. But when you apply VSEPR theory that tries to keep these bonding pairs as far away from each other as possible, in 3 dimensions you get this geometry, where the angle is 109.5 degrees. I do want you to know that angle. It's not 90. This is 90 up here. This is 109.5. And so you have a triangle here. You have one through here that goes up to here, and you have one in the back here, and then you have one below. And that's why it's called tetrahedral. Tetra means 4, and hedral means sided. There are 4 sides to this molecule. This is one side. This is the other side. There's a side behind here, and then the side beneath. Tetrahedral. So again, you get the Lewis structure, but to get the geometry, you have to apply valence shell electron pair repulsion theory. And when you do that, you find out the best geometry for the angle between and the way we would write this is angle HCH is 109.5 degrees. All right. Next one. Now we're getting into something that's a little different. So you look at ammonia and you say, yeah, we did ammonia. Ammonia had 5 valence electrons for nitrogen, 3 hydrogens, each one has 1. We had 8. And when we do the Lewis structure, it looks like this. There's a lone pair here, and then there's a bonding pair on this hydrogen, bonding pair on this hydrogen, bonding pair on that hydrogen. That's the Lewis structure. So here's where it's a little different. The total number of things, the total number of pairs of electrons coming off the central atom is 4. Well, if we have four things coming off the central atom and we want to keep them as far away from each other as possible, we would get this tetrahedral structure. So let me erase this now so you can see that. Let me erase all of this. Okay, so it's tetrahedral, the structure is. But what's different about this versus, what's different about this than ammonia is we don't have a bonding pair here. That bonding pair is gone. And in its place is a lone pair. So that's what we have here with ammonia. There's a lone pair. Well, the lone pair of electrons is the most repulsive of all the valence shell electron pairs. It wants its own space. So here it is. There's the lone pair, and we generally draw a balloon around it like that to say, hi, this is highly repulsive. Well, because it's so repulsive, it forces the bonding pairs closer together. So normally in a true tetrahedral, if these were all bonding pairs, the angle would be 109.5 degrees. But because you have this big repulsive lone pair, it forces the bonding pairs closer together, and the angle between the hydrogens, the angle between the hydrogen, the nitrogen, and the hydrogen is 107 degrees. A lone pair is more electronegative with a greater electron repulsion. That's what you need to know. So, yes, it's four things coming off the central atom. So the way I write this is A stands for the central atom, X stands for the bonding pairs coming off, and now we have a lone pair, E. And so there are four things coming off. Because there's four things coming off, we do arrange the electron pairs in a tetrahedral. There's bonding pairs here, bonding pair here, bonding pair here, and the lone pair. But you can't see the lone pair. It's invisible. So when we go to explain this geometry, we only explain it based on the bonding pairs. And so it looks like a pyramid because this is at the top of the pyramid. The nitrogen, the hydrogens are below. So we call this trigonal pyramidal. It's not flat anymore. It's not trigonal planar. It's trigonal pyramidal. So again, what's the difference between this and boron trifluoride? Well, let's look at boron trifluoride. Let's go back and look at it. So boron trifluoride, it doesn't have a lone pair. It was three bonding pairs. Bonding pair here, bonding pair here, bonding pair here. So that's why it's flat. But ammonia, you have four things coming off. You've got the three bonding pairs just like boron trifluoride, but you also have a lone pair that they don't show because it's invisible up here. And that changes the structure from trigonal planar to trigonal pyramidal. All right, let's look at the next one. The next one is water. And so, let's go back. So here's what I know about water. Students write the Lewis structure and they go, okay, I can do the Lewis structure for water, and it looks like this. And then they go, oh, the geometry is linear. That's what they want to say. It's linear. No, it's not linear. And the reason why it's not linear is you have a lone pair here and a lone pair here. So your classification, if I was going to classify this, I would say A stands for the central atom, oxygen. There are two bonding pairs, which I call X, and there's two lone pairs called E here. AX2, E2. So when you total this up, it's still four things coming off the central atom. So we still have a tetrahedral arrangement of the electrons. There's an electron pair here. There's an electron pair here. These are lone pairs. And then you have a bonding pair here and a bonding pair here. So because it's four things coming off the central atom, you still take a tetrahedral geometry. And here's what it looks like. Here's the bonding pair for this hydrogen, bonding pair for this. Now you have two lone pairs, two balloons, one here and one here. Well, that forces the angle even closer together. So for ammonia, with one lone pair off the central atom, it was 107 degrees. With two lone pairs off the central atom, the angle's now 104.5. These two lone pairs force the bonding pairs between the hydrogens to be closer together. So the angle between the hydrogen, the oxygen, and the hydrogen is 104.5 degrees. And it's either, I want you to memorize that angle. It's really important. This is why ice floats as a solid. Most of the time the solid is more dense than the liquid, but because of this angle and the way water bonds with another water molecule, it actually creates voids and makes ice less dense than liquid water. So it's really important. It also comes into play when you start talking about DNA and the double helix. So important thing, hydrogen bonding and this geometry make it a very important structure. So again, what you see with the naked eye, without the lone pairs are invisible, you have a bent or angular structure. We're going to use the word bent in this class, but bent or angular. So again, the actual geometry, the molecular geometry, as we say, the molecular geometry, let's get specific. The molecular geometry, or they also call it the shape, is bent. Now you say, what's this called when it's like a tetrahedral here? You call that the electron domain geometry. Electron domain, or ED for short. Electron domain geometry. Now, you say, is the electron domain geometry and the molecular geometry ever the same? Yeah, we saw that. Before we got into these lone pairs, let's go back. Let's look at methane. For methane that has all bonding pairs only coming off the central atom, the electron domain geometry and the molecular shape or geometry is tetrahedral. So if nothing but bonding pairs come off the central atom, then the electron domain geometry and the molecular geometry are the same. But if there is a lone pair on the central atom, the electron domain geometry and the molecular geometry will be different. So the electron domain geometry for ammonia is tetrahedral. But the actual shape, the molecular geometry of what you can see with the bonding pairs only, says it's trigonoplanar. I don't know if they test you on electron domain geometries. We do in Chem 170, Gen Chem 1, but I think for Chem 140, you just need to know the molecular geometries. But I think it's important that you've got to get the electron domain geometry correct in order to get the molecular geometry correct. So here's a summary of the different possibilities. So this is what I want to say. Instead of memorizing all this, this is what I say. X stands for the bonded atoms and E stands for the non-bonding. So if it's AX2 only, it's definitely going to be linear. That's like carbon dioxide. So let's look at carbon dioxide again. Looks like this. Lone pair here, two lone. But looking at the central atom, A stands for carbon, X2 stands for this double bond, and another X stands for this double bond. So here's something to remember. This is important. I haven't brought it up. It doesn't matter off the central atom if it's a single, double, or triple bond. That is considered an X. It's just a bonding group. So even though there's a total of 2, 4, 6, 8 electrons coming off the carbon, we call it AX2 because VSEPR does not distinguish between a single, double, or triple bond. So that's AX2. When we look at sulfur trioxide, it actually, if you did the Lewis structure, you'd find out it has a resonance. And here's why it's cool about this. It doesn't matter if you draw any of the resonance structures. You can draw all 3 of them. All right? It would look like this. And I'm not filling out the rest of it. But it does have resonance off the central atom. Notice it doesn't matter, according to VSEPR, these are all AX3. There's 1 group, 2 groups, 3 groups. Doesn't matter if it's single, double, or triple bond. So AX3, the geometry, the molecular geometry is going to be trigonal planar. Now, this one, first time we've seen it, this is sulfur with a double bond on an oxygen here and a single bond on this oxygen, and there's a lone pair on the oxygen, or on the sulfur. So that's called AX2E. X is this, and this is a non-bonding group. So I would call this AX2E. The E stands for this, the X2 stands for that. And again, what you see with the bonding group only is this group here, or that angle, and that's called bent. Again, this part up here is invisible. So go through these, make sure you know them. You're all going to be tested on geometries. Geometries are really important. They determine whether the molecule is polar or non-polar, not just the bond, the entire molecule. So up to this point, everything we've been talking about as far as polarity goes is bond polarity, the unequal sharing of electrons between like hydrogen and fluorine, and that fluorine's being more electronegative than the electrons are being pulled towards the fluorine. What we're talking about here is, yes, you have polar bonds on sulfur trioxide, but if I add up all these arrows here, they cancel each other out, and the molecule itself is nonpolar. So you have bond polarity and molecular polarity. This is bond polarity, individual bonds, and then you look at the entire molecule, that's called molecular polarity, and that's going to be important. All right, so here's the procedures. I'm not going to read them to you. I'll just let you read through this. And again, the PowerPoint is in Blackboard, so you can also print that off or pull that up while you're watching this video if you need to spend more time on the particular slides. But all I'll say here, again, what is this? This is what I would call AX2. This is AX3. And this is AX4. When it's just bonding pairs coming off the central atom, these are the main groupings. And then the ones that you have to know here are bent, where it's like AX2E or AX2E2. That's another one that's bent. Or trigonal pyramidal. That's when you have AX3E. All right, so this one is what happens when you have more than one central atom. So dimethyl ether, I don't expect you to know the formula for this, but we might write it this way. Okay, so that's what it would look like. And in this one, if we draw a structure, you have a methane here, or a methyl group here, and a methyl group here, and an oxygen in the center. So if we look at the oxygen in the center, there's going to be a lone pair here and a lone pair here. So off this, it's going to be off the oxygen, it's AX2E2. Well, off these carbons, it's AX4. It's carbon bonded to these three oxygen or these three hydrogens and this oxygen. So there's 4 bonding groups coming off that carbon. Same thing on this carbon here. It's AX4. So you've got 3 centers to this atom. You've got this carbon center, you've got this oxygen as a center, and you have this carbon as a center. So that's what they're showing, is that this particular molecule has 3 centers to it. Well, you know, if it's AX4, this is tetrahedral. You know, as far as the geometry goes, this is tetrahedral, because AX4 is tetrahedral. Same thing for this one. And then here, it is a tetrahedral electron arrangement. There's an X here, that's an X here, this is an E non-bonding pair here, and non-bonding pair here. But when we see AX2E2, we know that the geometry is bent. All right, and you said, man, I'm lost. Okay, if you're lost, let's go back. Let's go back and look at water. So when you look at water here, you have a non-bonding group, a non-bonding group, and a bonding group, and a bonding group. And this is the electron domain geometry, AX2E2. If it's AX2E2, the geometry is bent. Yes, it takes a tetrahedral electron domain shape. And notice it's got the lone pair here and the lone pair here coming off the oxygen. Instead of these being hydrogens, they're methyl groups, CH3 groups. So that's all that's different there. It still looks like water. It's just that instead of having hydrogens on the terminal ends, you have methyl groups on the terminal ends, which are tetrahedral. And then here it is on this oxygen, it's AX2E2. So that tells you that the geometry is bent. So it would look similar to water, but it's not water. You know, water looks like this. It's got let's do it this way: hydrogen here, oxygen up here, hydrogen down here, and a lone pair out here, and a lone pair back through here. So that's this part and this part. But instead of being hydrogens, you have methyl groups here. So it's still bent overall. Geometry is bent, but on each of those carbons, it would be tetrahedral. All right, so if you understood everything I've said here, you should be able to do the geometries of all of these substances. Okay, so let's see if you can do it. Stop here, draw them yourself, and then I'll talk about them, and then you can see if it matches up or not. All right, so first things first, add up your total number of valence electrons. Phosphorus in group 15 has 5 valence electrons. Chlorine's in group 17 has 7 valence electrons. There's 3 of them, so 3 times 7. So we're dealing with a 26 valence electron system. We know phosphorus is less electronegative than chlorine, so phosphorus goes in the center. Chlorines go around it. We know there's at least one bond between the phosphorus and the chlorines. We know each one of these chlorines has to have 8 valence electrons around it. So we're going to put 3 lone pairs around each one of the chlorines. All right, so this is 8 around each chlorine. That's 24. We got to have 26. The other 2 electrons go right there. So phosphorus feels like it has 8. Each chlorine feels like it has 8. We have a total of 26 valence electrons in the system. So we know that's the proper Lewis structure. Now, we apply VSEPR theory to this. We know that off the phosphorus, that atom is AX2E2. Or no, it's AX. Oops, I missed one. What was I thinking? I was really off. It's AX3E. I guess I was stuck on the water. All right, and you say, how'd you get that? This is an X. That's a single bond. That's an X. That's a single bond. That's an X. That's a single bond. And then we have a lone pair here. If it's AX3, we know that the geometry should be trigonal pyramidal. And you go, how do you know that? Well, you have to memorize that part. Trigonal pyramidal. I ran out of room there. So that tells me phosphorus goes here, and these hydrogen or these chlorines are down here like this. One's coming out the board, one's going back behind the board dash line, the lone pair right there. Trigonal pyramidal. That's what you have to be able to do. Now, one other thing, while you're doing these, think about bond polarity. You know that chlorine's more electronegative than the phosphorus, so the electrons are being pulled towards the more electronegative chlorines. That's going to be in the next section, so that's why I'm just setting you up for that. When you're doing molecular geometries, apply electronegativity differences to determine what type of bond do you have, because in the end you're going to tell me all these arrows are pointing in a general downward direction, and if you see this overall resultant force going in one particular direction, you'll tell me that the molecule itself is polar. So molecular polarity, you must have polar covalent bonds, but you also have to have the proper geometry. So that's where we're going with this is you use the Lewis structure to determine the three-dimensional geometry. You use electronegativity differences to determine bond polarity. You put the geometry and the bond polarity together, and you can tell me if the molecule itself is polar. And we're going to see more practice on that. All right, let me erase all this, and we'll do the next one. Let's see what that does. It's not any better, really. All right, I'm erasing all of this. I thought I was choosing something that just erases it. I don't have to do it individually like this, but not there yet. All right, so let's look at the next one. We're looking at sulfur dioxide. So the first thing is total up your valence electrons, 6 for this, plus 2 times 6 for that. We're dealing with 18 valence electrons. Sulfur is the least electronegative, so we put it in the center. And you're going to find out it's a double bond on one oxygen and a single bond on the other oxygen. And there's resonance, so there's a double bond on this oxygen, single bond on this one. There's got to be 2 lone pairs here. There's got to be 3 lone pairs on that oxygen. So down here it's 2 lone on the double bonded oxygen, 3 lone pairs on the single bonded oxygen. Now that's 16 electrons. The 18 electrons, the other 2 electrons have to go on the sulfur, so they'll go here and here, and then we would put double-headed arrows between the 2 to say resonance is occurring. All right, what else you should do, let's just go ahead and do this. You should draw arrows going towards the more electronegative oxygen. So you do have polar covalent bonds. The electrons are spending more time around the oxygens than the sulfur. Just keep that in mind. All right, now we're going to apply VSEPR theory, valence shell electron pair repulsion theory. So your classification here is AX2E. You say, how'd you get that? Well, that's a bonding pair, that's a bonding group, that's a non-bonding group. And it doesn't matter which one of these Lewis structures you choose, you're going to come up with the same classification. So 3 things coming off the central atom tells me it should look like a triangle. Double bond down here, single bond on this one, and a lone pair up here. The lone pair is invisible, so the geometry is bent because you're just seeing from here to here. This is invisible. But you have to put the lone pair in correctly in order to get the correct geometry. So it is bent. I know it's bent as soon as I write this down. If you want to work to that, being able to do that, you'll be in great shape. But if you draw it correctly, you could also see that it's bent here. It's not linear. And I'll leave that as a multiple choice answer on a test. It is not linear. It looks linear when you do the Lewis structure, but that lone pair makes a difference. So that's how I know if you understand VSEPR theory or not. And then again, these are polar covalent bonds. The overall resultant vector is in that direction. That's the way the arrows are pointing in general. And so sulfur dioxide is a polar molecule. All right, that's what you're doing. Let's see. Let's do... I think I'll stop. Let's see. Do I want to stop here? I want to erase some of this. Let's see what happens. I'm trying to figure out if I can do a better job erasing. I mean, we'll do one more, but that's the process, and you've got to get good at the process through practice. And so let's do one more just to make sure that we know what we're doing. All right, let's look at phosphorus trihydride. So this has 5 valence electrons plus 3 times 1 for each hydrogen. We're totals 8 valence electrons. So you know phosphorus goes in the center because hydrogen cannot. You know there's at least one bond between each hydrogen and phosphorus. And the other 2 electrons go here. That's 8. Each line represents a shared pair. And so that's 6 plus this lone pair here is 8. That is the correct Lewis structure. And then the next thing is that you apply VSEPR. You would tell me this is AX3E. There's 4 things coming off total. There's 1, there's 2, there's 3, there's 4. 4 things coming off tells you to take a tetrahedral arrangement. So there's a hydrogen coming here, there's hydrogen coming out the board at you, there's a hydrogen going back through the board like that, and there's a lone pair here. When I see it's AX3 and I draw this picture, I can see these 3 hydrogens are on the same plane. This phosphorus is above the plane. So that tells me that the geometry is trigonal pyramidal. And I'm done. And I would talk about the polarity, but I think they're pretty close. I think hydrogen and phosphorus is so close that it's actually considered. I think it's between, the difference in electronegativity is between 0 and 0.4, and that would make it a non-polar type bond. So there would be a slight polar. I will say this. Overall, this is a slightly polar molecule. It'd be in this direction because of this lone pair here. That's what I would say. That's a little beyond the scope of Chem 140, but it's something worth mentioning. All right, we're at an hour. I think I'll stop here, and you can watch this video along with some other ones I'll post in the Blackboard announcement. You need to watch these videos and try doing the homework before you come to the next class. I hope this helps. And if you need more help, it's time to email, get on bookings and schedule an appointment with me, or go see the tutor, but you need somebody to dialogue with to talk through this. All right, thank you.